But this is Douglas. Doug, a quick question from Mark about the experiment there. I'm assuming or intuiting that the direction of rotation of the bowl is the same as the spin of the gyro. Is that true or not?
Yeah, it's the same direction as the spin of the gyro, and the gyro's precession is the same. So there's a lot of spins going on here. There's the spin of the gyro around its axis, and then there's the spin of the axis, which is its precession, and then there's the precession of the bowl, and they're all spinning in the same direction. And I just had a brain, storm. What if I put two, one on either side, both spinning in opposite directions? Would that move it forward?
Oh man, I love that idea. I completely love that idea. So what you're saying that as the gyroscope is decelerating, instead of it experiencing a counter rotational force, so that the entire disc spins in opposite direction to the present rotational direction of the gyroscope, it actually accelerates in the same direction, which would be counterintuitive to the frictional forces.
This is Mike Gamble. I'd like to comment on that. That's exactly what I'm doing.
Oh yes, show us. You have,
or tell us.
Do you have it right with you?
I have a demo model.
Oh, I should also ask, Douglas, was that everything?
I don't know how well you can see it on your box there, but there's two gyros in there.
Yes, thanks. I'll defer my other comments till after this.
Okay, thank you, sir.
So what does that do?
That does linear propulsion with two reciprocating gyros.
Okay, what kind of results have you seen?
I demoed that for Tom Valone at the coffee conference, and it does make propulsion.
Wow.
On what order of magnitude, and what is your test setup? Like, have you floated it in a bath of water?
No, just on a flat table.
And it loses weight, or is it moving along the table?
Moves along the table.
Okay, you should try it again. Just put it inside of a raft in a pool when the water's perfectly steady, and try it like that. That is that's the best way to test something like that, because when you're dealing with lots of shaking parts, it's possible to for it to inch along, just like some some robots use that process of like shaking, because it all depends on the mount.
It's pulsed.
Pendulum test with it showing that it has a constant displacement to one side of the gravitational attraction would really be the gold standard. It shows a constant acceleration.
Pendulum doesn't work as far as pulsing. It only works if you have a steady state. If you have it pulsing, it'll start swinging.
Well, actually, Roy Thornton proved it in 0 point energy raised to zero. What was it? Free energy raised to 0 point. It's a video online, and you can actually see the pendulum staying to one side of the normal. So in the 1990s.
I'm just very concerned with how it's attached to the table.
Yeah. Let me see if we.
Yeah, and I think Tom Valone is actually with us today.
Yeah.
So
he's familiar with it. He's got the videos.
You can go to www.futureenergy.org and get the link to Mike Gamble's video presentation at COPE 12, which is back in August. We were happy to give away the conference for free to everyone, and not too many people attended, but it was almost 300. I think we had a lot more than we would have in person if we were in Albuquerque. But suffice it to say that a few years ago, Mike predicted he could do it, and this year he did it. So I could actually share the screen and show you the video. This thing is so robust, it goes right across the flat table. This is not just inching along like all the other inertial repulsion attempts in the past history of this science.
If you're able to, that'd be wonderful. And welcome, Tom. Thank you for joining us.
And he's just holding the wires gingerly right above it. But this is the first trial run of the improved low mass version. And then we're trying to go for bigger gyros. Whenever Mike's ready, we'll order them. Instant replay. And this has been theoretically predicted the first round, he actually measured it, a force of 0.4 pounds of thrust, and he predicted it theoretically as well. So that's a journal article in the making.
Okay, that's exactly what I'm talking about. Yeah, I like the rollers that you have over there. That's probably a pretty accurate prediction. I would like to try it though in water.
Oh, sure.
Yeah, we could set that up. That doesn't look very difficult to do. Just get two motors. It's actually the exact same kind of gyroscope that I have over here.
Yeah, precessing gyros.
I would like to ask, is the motion of those two gyroscopes simply rotational, as in they would be rotating fairly centered to some axes, and they're simply having a different speed in one direction versus the other, or how is this force being generated? Can we clarify here?
Mike's got the whole thing. In fact, it's in part of a slideshow as well. And the whole presentation, 45-minute presentation, is online. And I can probably give you a link to it.
It is difference in the speed. It goes fast in one direction, slow in the other, and the gyros are rotating at 16,000 constant.
Okay, so that would make sense from the relativistic perspective too, in terms of the difference in the acceleration velocity based on the fact that it already has some stored angular momentum in each gyroscope.
Will it work on a pendulum?
It will swing.
Like constant force?
It's not constant, it's pulsed.
Oh. I've done a lot of experimenting with these kinds of systems, not necessarily with gyros, but with pendulum type machines.
Yeah. If it supplies DC, then a pendulum will work real good, but if it's pulsed, it doesn't work very good at all.
It doesn't matter as long as it moves your spacecraft forward, though, really.
That's the whole thing, is will it work?
It's the difference between AC and DC voltage. They both do the job, but one comes in spurts.
I guess the better question to be Mike, will this device produce a force in space?
Yes, that already does that.
He worked for
Boeing's got them on their equipment.
That was the start of our interest in getting him to work on the civilian version.
I used to work for Boeing, and they have on all their spacecraft, and well, not only Boeing, but all the aerospace, they have 4 big gyros, and all your geosync satellites have them on there for that very reason. You don't have to. You don't have.
There's 4 years of presentations on this topic.
Oh, wow. Yeah, that's fascinating. That's fascinating. I always thought the gyros on satellites were simply for orientation control, not necessarily for motion control or any kind of velocity.
They do both. If you spin the gyros opposite directions, you get torque. If you spin them in the same direction, you get linear.
Oh, this is the highlights of the presentation. It's all
well, thank you for sharing all this, Tom. This is wonderful.
Well, you can see the whole video is online, futureenergy.org. And you can see the link to it. It's all on YouTube, actually. 8 hours of the presentation, 2 days in a row.
Is there any momentum transferred from the spinning of the gyro to the forward motion, or
It's
the gyro?
It's a change in mass. The gyros add mass.
Well, you've got the moment of inertia to deal with. And he's got a master equation here too for the actual net force, but he deals with every moment of inertia first. I mean, Mike is meticulous.
And as he mentioned, the gyros are kept at a constant rotational speed, so they're not slowing down and transferring any of their energy in that way.
Little bit, but not much. It's fairly constant.
And this is probably one of the best equations, right, Mike? Force, peak force, and you've got the mass, the total mass, and the radius, and then T is the time in seconds for the oscillation, and it's 0.48 pounds. you went from 0.4 to 0.48, right?
Yep.
Improvement. So you got a half a pound of force to really propel things along. But this is theoretical, and then you measured the force and actually found it matched.
Yeah, the numbers are pretty good. And you can see on the chart there's a lot of background vibration.
Yeah, and that's what we're trying to reduce now. Acceleration versus direct.
I have a question about the motors that are running this thing. So I take it there must be some motors that are spinning the gyros.
Yes, there's
And
one
then-
motor on each one.
And then there's some other type of motor or some electromotive thing or solenoid thing that's jerking them back and forth.
Yeah.
How do you reciprocate them?
There's a servo. Tom, can you put the picture back up of the side view
Okay, that's
of the carriage?
yeah. That's one side view.
No, the real picture.
The
He
real
wants to see the servos.
okay.
Yeah.
Yeah, right there.
Left.
Okay, under the picture on the left where it says left side, you see the gyro up in the air with the black cylinder, which is the motor that spins the gyro. To the left is another little black square, which is the servo motor, which turns it. And these the two little blue boxes on the left-hand side are the servo motor controllers and power supplies. And the big blue box on the right is the data acquisition.
And I take it if you were not spinning the gyros, but only reciprocating them back and forth, nothing would happen?
It still generates a little bit of thrust, but not nearly as much. The numbers there, I did it both ways to answer that question.
Actually, here's an example, right, Mike?
Yeah.
Gyro's not.
Gyro's not running with 20-degree cycling, and
You got
it
another.
generates a little bit of thrust, and then it goes way up as soon as you turn the gyros on. Essentially, they add mass to the system.
And that's with it running. And you can see all the noise that
Yeah.
gyro
Yeah, the background noise goes way up.
acceleration. So this is just the first prototype, and we're working on smoothing everything out to make it a really robust system.
Yeah, there's the comparison right there. From 108, whoops, you had it there.
Back up. Got the one you want?
Yeah, yeah. Yeah,
Well, you're up to
The
290 now.
one circled in red, which is 300 millig's, is with the gyros not running, and it goes to 483 when you turn the gyros on. And they're adding mass in that one axis by the spinning.
I don't know if you call it mass, but
Well, inertia,
inertia.
one-dimensional mass.
Force. I think it was MA.
Just a follow-up question on that about the efficiency of the system. So if you were to, so it's exerting a certain force, and which you could presumably measure on a force meter.
Well, I have an accelerometer on the front that I use to measure it.
What is the efficiency, let's say, of the energy you're putting into the servo motors versus the amount of
Well, the
of
big
traction it
waste
can
is
produce?
spinning the gyros.
Work being done.
To spin up the gyros requires lots of force. Once you get them going, then the only power you're expending is the servo motors, which are a little more efficient, but the big loss is spinning the gyros.
And-
But
and
if you had very efficient bearings on your gyros, there aren't some kind of coupling of angular momentum transfer that would slow your gyros down if they had very good bearings.
It has ceramic ball bearings on there. They're from Gyroscopes Incorporated over in England is where we get them. And they're built very well. I'm amazed they hadn't torn the bearings out because the thing turns at 16,000. And we've put quite a few hours on them.
Thank you.
So the idea is that this effect is being caused by a relativistic conservation of some kind of, I don't know, relativistic energy. And also, I would definitely like to see this experiment done in a water tank to make sure that there's no friction with those wheels on the table or any sort of effect there.
You can
May
hold.
I present them? Go ahead. Sorry.
You can hold it in your hand, and there's vibration sideways, but there is no force. You can feel it. It's all in one direction.
I would like to present a simple water-free test because you probably don't want to stick that thing in water, and also it might rock back and forth in water, which could be an issue. I've seen a great video demonstration, and I don't know if it was real or not, but the way they demonstrated it was good. They took a bunch of ping pong balls, which are fairly rigid and fairly spherical, consistently sized, and laid them out on a table with enough spacing so that platform placed on top of, say, maybe 15 of them at once could easily move back and forth. It basically reduced the friction of the system. And then they placed the box that had a device very much like your own inside of it. And I say like your own only because we don't know what's inside the box, but it moved in the same type of way. And I think the ping pong balls and that rolling action of the device being placed on a board would help eliminate a lot of questions about friction, because the torque ratio of the friction there would be.
There's even a better. Yeah, well, there's even a better way. Use air hockey table.
Yeah.
Put
That's
a
a great
flat plate
idea.
on the bottom and use air hockey table.
Right.
Tom's been twisting my arm to do it.
I love that idea. It's a great idea, Tom.
Can't wait to buy one for him. You just got to say yes. And
Craigslist, eBay, somewhere. It's got to be cheap and available.
that's right.
Well, you could go to any of these video game parlors that have a hockey table and just rent it for an hour. They're like 4 by 8 feet.
What do we have to do to convince you to do that?
Yeah, what do we have to do to convince it?
Buy me some more time. I'm working round the clock. My wife's off the machine, and so I'm back in my office. I just got moved in here today.
Wow, okay.
Matter of fact, I'm doing calculations on stuff right now while the conference is going on.
And the bigger gyros are going to be ordered when?
Yeah. I wish I could give you an answer on that. I'm trying to order the servos right now.
Okay, whenever you're ready, Mike, we'll get this to a bigger scale where it's.
Well, I'm working on it.
I hope so.
Yeah, I'm very excited to try that experiment as well. I'll try it inside of a bathtub if I can find a big enough, laminar water place to place it. But from what I was seeing in this last experiment, I do think it would work. Are they spinning in opposite directions, or they're spinning in the same direction?
For linear force, the gyros have to spin in the same direction. If you spin them opposite, you get twist.
Okay, are they? I'm talking about in relation to the axis of motion. Are they spinning in the same direction? Because if they're facing each other 90 degrees, they would be spinning in opposite directions, but relative to the axis of motion, will be spinning in the same direction. So
Correct. Correct.
So, are they spinning like this? Mike, are they spinning like this together?
Yes.
Okay, so that's opposite direction.
Yes.
They're actually spinning on opposite direction based on their axis of motion.
Yeah.
Which is what I talked about earlier.
Yeah.
Okay.
And if you have them spinning alternately, then the thing just twists.
It'll just
back
spin around.
and forth
Yeah.
instead of moves.
Yeah, that makes sense. And you said that there is servos involved as well. What are the servos doing?
They're the ones that are torquing it. Supply the twist. It twists between 0 and 20 degrees. There's 20 degrees twist.
Up and
Back and forth.
up and down, or is it going, left and right?
Yeah, left and right.
Left and right. Okay. Perfect.
It looks like swimming,
Like it swims.
swimming breaststroke.
Yeah, there you go. Perfect.
Okay, very cool. Okay, so we'll try that. Have you tried more degrees than 20 or?
Oh yeah, I've run 20 is the optimum. In my presentation there for Tom, I do the whole optimizing game for speed, velocity, torque, and the whole thing.
Okay, I probably have enough equipment over here minus one gyroscope to set this up by tomorrow. But I have to take my remote control airplane apart to salvage some servos.
That's where they come from.
Yeah, that is where they come from. But like they mentioned earlier, you really can set that entire apparatus on a flotation device or on a board that you'd put on a air hockey table.
Yeah, well, that's the plan.
We actually had Steve Hampton do it for his presentation. We had 2 inertial propulsion presentations in the same day. So in fact, if you go to the URL I just posted, there's another one just for the entire conference, and that would probably be a double benefit. So here's the entire conference. I'll chat you that information too. That's the entire one, and then there's the one for Mike Gamble's. Steve Hampton actually did a bathtub demo at the very end of his. In fact, I could probably show you that too if you want.
Oh yeah, that would be amazing. That's what this conference is all about.
Okay. Yeah, he had a double rail that he attached his to. So okay, I've got it queued up right here. And
Mike, was your machine inspired at all by Sandy Kidd?
No, about 5 years ago, I presented a history of Boeing gyroscopes at Tom's conference there, and everybody says he wanted me to build one. So I built a model of it. The release from Boeing shows the big gyros. We had 4 big gyros that generated a couple 100 pounds of thrust. Boeing has been using these things since the 60s. Like I said, they're all on satellites for propulsion, and they call it station keeping because you don't have to store propellant, you just spin up the gyros.
So I got Steve Hampton's if you want to see it. I guess I'll turn the sound for it too. And Glenn Robertson from NASA helped him do the analysis. Okay, showing you the data first.
And maybe that's what we need to do the salsophone experiment.
Glenn Robertson's contact. Glenn was a consultant for this project. And Glenn ran his own conferences for years too.
Oh, do you think if you had 4 sets of gyroscopes, you'd be able to get a continuous motion?
Not necessarily. They're all pulsed, but it's like a car or internal combustion engine. They put a flywheel on the back side, but there's actual like 8 power pulses for a V8 or 4 or 1. And then the flywheel smooths it out. That flywheel is the inertia of the vehicle.
Right. It's part of the inertia. The car moving is also
Yes.
Inertia.
If you've seen my slides there, I calculate all the inertia for the individual parts.
But it definitely would smooth it out a bit, having 2 pulses, sort of like, higher frequency AC is more energy.
Yes.
Oh, okay.
Yep. The frequency of resonance increases.
It's like the Model T engine, right? 2-cylinder to 4-cylinder to 6 to 8. Then we got the V12.
There you go.
Come on, V12.
Now, is this Mike's also? And the reason I ask is when I do the write-up for this, I'm going to try and include as much as I can.
Yes.
No, this is Steve Hampton.
Okay.
I can give you.
He's
I
using
call it-
rotating weights rather than gyroscopes.
Right.
You can see the weights on the bottom rotating.
And the
And
bathtub.
he uses a solenoid for rectification.
Yeah. And the bathtub's coming up next. And by popular demand, the water boat bathtub. Here we go. Your
Yeah.
wish is our command.
Wow.
We got two of them that work the same way, and I give credit to Roy Thornton, who started with a canoe. The canoe is the best one because it has no chance of benefiting from the backward stroke. And here's the pendulum test to improve his video. But
Thank you so much for showing these. This is
Sure.
wonderful.
Put in a plug for the conference.
yeah, that's right.
Well, I will. I'll put in a plug and links, and we'll have all sorts of info there.
Yeah, futureenergy.org has the whole story and
You
the
see,
program and the papers
Yeah.
and slideshow.
you see it pulsing
Yeah, this is, I didn't think that was,
when you do the pendulum test. It starts swinging because of the pulsing.
right. But Roy Thornton stayed on one side in that video, 300 races. This is not a very good demo, in my opinion. Okay, so that's it. That was the end of that presentation. Okay. Well, I've got a research project tonight to finish, and I'm glad I was able to support Mike Gamble in his hand waving. So and we look
yes.
forward to bigger gyros next time. Bigger and better, onward and upward.
Well, thank you again, Tom.
Very welcome.
Yes, thank Michael for all that. I just wanted to mention that we will be getting together in the lab in December, and Jeremiah is going to be flying in. Jeremy might be there. Wayne might come in. So if anyone wants to come to our lab in Hawthorne, New Jersey, and be a part of these experiments, we did rent out a guest house. Somebody donated some money, so we're able to actually get things moving over here. And we're trying pretty much every experiment we can think of that we can do in a reasonable amount of time and budget. And Mike, your experiment seems extremely interesting. I'm actually trying to get those gyroscopes right now so we could have them here on time. I use the exact same gyroscope myself. I find them to be
Yes.
good. And the servo thing, that's very simple. We'll be able to contact you about how to set that all up. I'm pretty familiar with using RC airplanes and servos and all that stuff. So set that up pretty easily for it to go back and forth. Have the battery on board and have really like a self-propelled device that is irrefutable.
Yeah.
And if we get the thing to turn, that would be even cooler.
Yeah.
Well,
like I
and
said,
yeah,
Tom's been trying to get me to get it on an air hockey table, but I had to vacate my office for 2 months because my wife does teaching, and with the COVID bug here, she had to use my office to do her schooling. So I'm just getting back up to speed again.
How much does that whole thing weigh, by the way?
That about a couple of pounds.
So you're going to have a pretty large surface area in order for it to float. You might be better off just putting it in a tub in a large pool or something.
I already did the calculations on it. It takes about 18 square inches to lift it.
That's it?
Yeah.
Okay. You can try it out. You got to get a big table so you have room to move around.
Well,
Yeah.
there's a lot of these chunky cheeses places, video game pool halls, whatever you want to call it.
The 4-person one, that's what you want to get. The really big
Yeah.
table. Rent it
well,
out.
you know,
They have the 4x8 tables, which is plenty big enough.